Hey there coders, welcome back to another exciting episode in our Rust programming series. In today's video, we are diving into fascinating world of pointers in Rust. Let's get started. So, what are pointers? Pointers are variables that store memory addresses in Rust. They are at heart of how we manage memory safely and efficiently. You should refer to the Rust of official documentation. It provides in-depth knowledge about all Rust related topics. Now, key types of pointers in Rust. There are mainly three types of pointers in Rust. They are references, raw pointers, and smart pointers. Let's start with box pointer, which is used for heap allocation. It is great when your data is too large or when the size of data is not known at compile time. Let's open up your editor and see how it works. Let's create one variable x box 5. This creates a box smart pointer and allocates the value 5 on the heap. The pointer itself is stored on the stack. The box new function ensures that the value is managed and deallocated safely when it goes out of scope. Now print the value. By star x. Now the star x syntax dereferences the box pointer to access the actual value stored in the heap. Here it prints 5. Let's run the program and see the output. Here x is 5. Dereferencing a box is safe because Rust guarantees that the memory is valid. Next up, dereferencing. This is how you access the value a reference points to. Let's remove this. Let's create one variable y equals 10 and z is equals to reference to y. Here create a immutable reference to the variable y. This reference z does not own y but borrows it. Now print it. Print z star z. The star z syntax dereferences the reference z, allowing us to access the value of y. This prints 10. Let's run the program and see the output. Z is 10. Now, shared ownership with RC. Want multiple owners for the same data. That's where RC comes in. Let's see how it works. But first remove this and import RC as from standard library. RC from standard. A equals RC colon. Here creates an RC smart pointer to the value 5. The data is allocated on the heap and RC manages its reference count. Let's create one more variable. Let b equals. This creates another reference to the same data as a. The reference count is incremented, but the value is not duplicated. Let's create one more variable. Let's see. Similarly, creates a third reference to the same data. The reference count increases to 3, but the value is not duplicated yet. Now print all the value and see the output. Here, don't forget to dereference it, everything. Here dereferences A, B and C to access the shared value, that is 5. All three references point to the same memory. Now print reference count. Prints the reference count. This line prints the reference count, which is 3 in this case, as there are 3 active references, A, B and C. Let's see the output. Reference count is 3. Now let's make RC thread safe using ARC. First remove this. So remove also this. Import ARC from standard sync library. And you import thread also. Now create one variable value equals, let's say 10. Here wraps the value 10 in an arc, a thread safer reference counted pointer. Allow multiple threads to share ownership of the same data. Now in this line of code, here let value, each thread receives a cloned reference to the arc. The reference count increases and threads spawn creates a new thread. The move keyword transfer ownership of the arc reference into the thread. Now print value. First here from for handle in handlers, enter. Let's see from here. Each thread safely accesses the shared value using the dereference operator. The star is dereference operator, and handle.join.unwrap waits for all thread to complete execution before continuing. Let's run the program and see. Value is 10, 10, 10 because the range is 0 to 3. Now interior mutability with RefCell needs to, if you need to mutate data even when it is borrowed immutable, enter RefCell. Let's see how it works. Remove all this. Also remove this and import it from standard library. RefCell. Let's create one variable called data equals RefCell new 10. Here wraps the value of 10 in a RefCell which enforces borrowing rules at runtime. Now let's create one mutable borrowed sorry borrowed data equals data dot borrow mute. Borrowing in this line, we borrowing mutably allows modifying the values inside the RefCell. And after that, we take borrowed data and increase it by 1. Here dereferences borrowed data and increments the value by 1. Now we have to print the updated value. Sorry, data dot borrow, here it's updated value. Here creates an immutable borrow to print the updated value, which is now 6, which is now 11, sorry, because we have incremented the value of 10 as 11 here in the block. Now combining RC and RefCell. Combine RC and RefCell to share ownership and allow runtime mutability. Import RC also from standard library std_rc and remove this data is select data clone equals RC clone here creates a shared reference to the RefCell. Now increment here, not RefCell, here it is R C colon new, and here it is, sorry, RefCell new 10. In this line, combines RC for shared ownership and RefCell for interior mutability. Now increment data by asterisk data clone dot borrow dot mute and increment it by 1. Here mutably borrows the RefCell and increment its value by 1. Now print the updated value. Data dot borrow with, let's print, and now data is 11. Here reads and prints the updated value, which is 11. Now see the comparison table between, here is the comparison table between box RC and box RC arc and RefCell. In box the ownership is single, in RC the ownership is shared, in arc ownership is also shared, and RefCell in single. Thread safety is not available in box, not available in RC, available in arc, also not available in RefCell. Mutability is at compile time, immutable only, and it runtime check. Use cases: heap storage, share single thread, share multiple thread, interior mutability. And that's all for this video. I will see you next one. Let's keep building with Rust. Thank you.